Alrighty. Good afternoon, everyone. Thank you for joining us. This is our August webinar, part of the International Society for Bone Morphometry. This is an initiative from the Early Career Investigation Committee. The ISBM, we're focused on all aspects of quantitative assessment of bone across scales. We host leadership panels on early career opportunities as this one, and we also have working groups which have a wide variety of topics such as HRQ, CT, advancing protocols and clinical research, spatial transcriptomics in skeletal tissues, imaging analysis of nerves and bone, and bone micro and ultrastructure assessment. This initiative is part of the Early Career Investigation Committee, which is led by Dr. Wale and Dr. Agrawal. And we want to remind you that next month seminar, it's going to be in bone metastasis by Dr. Sorkin Park from Korea University. It'll take place on September the 25th at 10 a.m. Central Time. We also want to remind you to save the date. Next year, the meeting will be in London from July 4th to 7th. And we have our keynote speaker, Dr. Krista Mais, which is going to be joining us. And if you want to follow our news or updates, you can follow the new page in LinkedIn, which this is the homepage in case you want to join us. And we want to thank our corporate partner AstraZeneca for their support of this webinar series. With that, please join me in welcoming Dr. Jepsen. Dr. Jepsen is is an associate dean from research and a professor of orthopedic surgery at the University of Michigan Medical School, and as well as a professor in biomedical engineering. Dr. Jepsen is a leader in the field of bone biomechanics, whose career has been dedicated to unraveling the complexities of skeletal adaptation, growth, and aging. His innovative research bridges advanced approaches with translational insights, exploring how bone architecture not only shapes biomechanical function, but also influences fracture risk across the lifespan. By integrating findings from animal models and human studies, Dr. Jepsen's work is helping us to identify crucial factors that contribute to bone quality, and today he'll guide us through the fascinating interaction between bone form and function, offering new perspective on how personalized approaches could one day reduce skeletal fracture risk and improve lifelong bone health. Please join me in welcoming Dr. Karl Jepsen.
Carlos, thank you so much for the invitation, and thanks for the Lit Career Investigator Committee for this invitation. I really appreciate it. I guess first I would just like to say good morning to those in the out in the Pacific Coast, good evening to those in Central Europe, and I guess good afternoon for those in the Midwest. For those who don't know where Ann Arbor, Michigan is, it's where this little gold star is, I guess maize and blue star are sitting right there. And we are somewhere between Canada and Mexico and kind of in the middle, okay? And so I am just going to give a kind of a high-level overview of what we do in biomechanical analyses and how we utilize information on bone architecture that may be of interest to some people on this call. I did see some names in here that I haven't talked to in a couple decades, so it's good to see those individuals and some people who are more proximal to the work that that I do. It's good to see everyone here. And then hopefully at the end, we'll have some time for open discussion. So in terms of disclosure, I really don't have anything related to this presentation. I do have a relationship with BioMarin Pharmaceutical, but it's not really related to the content of this presentation. So what I'm going to talk about today and what I was asked to talk about is really how we go about taking morphological data and trying to make sense of it. And most of what I do is really related to overall function. And for me, function is mechanical strength. And for others, it may be a different level of function. But so I just wanted to put that context out there because that might change the interpretation of what I talk about. I just also want to disclose these are my personal opinions. There really are no standardized methods for doing this. I think everyone kind of has to look at the data for themselves and to kind of find their way. But if for any kind of takeaway message from this discussion is try not to take morphological data at face value. There's a lot to dig into and try to find the story. Okay, and what I hope to do today is to provide you some tips and tricks that we have used and we've learned along the way that some people may find helpful as they start looking at their data. So as far as an agenda, I'm just going to present 2 guideline papers there and in the field, and this is just in terms of for reference. And then I'm going to go back a little bit in biomechanical mechanisms. I'm not sure the full background of everyone on this call, but it's really important to understand some basic biomechanical principles. And for that, because that's really important for interpreting morphological data of hard tissues like bone. And also talk about something we're calling contextualized biomechanics. And when we get to that slide, I'll explain what that means, and hopefully it makes sense to folks. And then we're going to move over into some systematic analyses that we're doing. And I'm going to try keeping this as simple as I can and not get too weedy. Okay, we'll talk a little bit about body size adjustments and complex adaptive systems and why that's important. And then I'll just end with an example that hopefully will try to pull some of this information together, and then provide some references and resources, and we'll open up for discussion. Okay, with that, there's a couple of guideline papers out there. Most people, I think, know the guidelines for the assessment of bone microstructure using microcomputed tomography. That's been the literature now. It seems like just yesterday, but it was 15 years ago. And then about a decade ago, there was also another paper on establishing biomechanical mechanisms in mouse models. And the information on that is largely the basis of what I'm going to be talking about today. I'm going to mostly talk about cortical bone, although I'll end with some ideas about what people can do in terms of cortical cancellous structures. Similar principles can be applied to that. It just makes it a little bit more easier to kind of get through a whole session today just in cortical bone, because there's a lot to kind of go through. Okay, so this information, I can provide these slides to anyone who would want them. Okay, so given the the society that I'm speaking to in the National Society of Bone Morphometry, it's an easy task to kind of bring people up to speed on microcomputed tomography, which is kind of a cornerstone of what we are doing. In terms of history, the University of Michigan was, one of the originators of that technology, which is, we're very proud of that. That Steve Goldstein, next to what at the time was the first micro CT system to study bone. Second system, the first one was actually developed by Ford Motor Company. Since that time, a lot of commercial systems have been developed, and we have things, commercial systems for micro CT as well as nano CT. But what's great about this technology is it can, as everyone on the call knows, it can generate 3D images and the ability to quantify many architectural traits. And in this little column here, you can see there's just a short list of some of the many things that we can get very, very quickly. So some of the questions that come up is like, so what data are you going to follow? What are you going to look at? Should I focus on the things that are different? Should I focus on the things that are not different? And, with so much opportunity to kind of look at this, how do I pull together a story? Because in general, one of the goals that, many of us do, whether it's a preclinical model or even using clinical data, we're trying to understand the impact of a perturbation, let's say, on bone strength. And that's generally what I'm looking at, but it could be another functional assay as well. And the morphological changes often give you clues to how that bone strength has changed, arising from that either genetic perturbation or aging or looking at diet or exercise. Okay, and then our job is to connect those phenotypic changes ultimately with the underlying biology. So when I'm trying to do biomechanical mechanisms, this is what's in my head is this big sheet. It's not unlike what, if you're looking at molecular mechanisms, you can try to draw these connections among, different elements of a molecular mechanism. But we can also do this in a very systematic way for biomechanical mechanisms, which is really trying to understand how changes here at the cellular level ultimately reach up to strength and work to fracture. So I tend to approach this like a detective, okay? And, like any good detective story, you need to understand who are the major players, how are they involved? Can you point to a mechanism like the whodunit kind of concept? and then to figure out, okay, what's the next question, or what's the cliffhanger? Okay, what is your next step following this first investigation? So as a spoiler alert, you're going to be playing the detective, and that's what we're going to do today. We're going to try to figure out, how do we define the terms we want to look at? How do we understand the connections that exist within the data? How do we piece it together ultimately to tell this story? Okay, and again, I said this previously, is like, don't take data at face value. Bone is a really smart material, and it has an ability to adapt quite strongly. And when perturbations happen, part of the job here, the detective work, is trying to figure out all the other changes that have occurred in addition to, let's say, a primary perturbation that may exist within the tissue. Okay, so ultimately your job is to listen to the data. And that's, if I can give you a couple tips and tricks along the way and get you to pause a little bit with that big long list of architectural traits that we can generate, then I think this is a worthwhile effort today, for spending this 1 hour. Okay, so just in terms of background, I think most people on this call are familiar with biomechanical, basic mechanical principles, but I'm gonna go through some of these. In this little image here, hopefully you can see my cursor that's moving. There's a mouse bone sitting here. It's under a 4-point bending jig. And what we do is literally just move the upper loading platens down into the bone. That displacement is measured. The load the resistance of that bone produces a load on the load cell below it. And then we plot that load versus deflection, and we get a curve that looks more like this little black line that's right here. The initial part of that, is generally straight. That's the stiffness of the bone. That tells you something about, if I apply 1 millimeter, it's going to, this is the kind of load of resistance to that deflection. It gets to a certain point where there's enough damage that's induced to the bone, and it starts to yield. Okay, so that's what this little peeling off part that you see here. And then finally it ends up breaking, okay, or it's which is like its ultimate whole bone strength, or its maximum load. And one property that a lot of people don't measure, but I have found to be very important, is what's called post-yield deflection, or this PYD. And we measure it by taking the deflection at the failure, and the difference between that and the yield deflection. And that's getting you a sense of how much more deflection does this bone go to fracture after it reaches the yield point. Work to fracture is the fourth variable that I look at, okay? And that's just simply the area under the curve. So you're just literally counting up all the area under this curve right here. You can see in this strain B, which would be considered ductile, you're gonna have a very large work to fracture, as opposed to this strain A, which is quite brittle. It's actually failing very, very quickly after it reaches the yield point. And so its work to fracture is very small. So when you look at that biomechanical mechanism, you start putting these together, you can see that stiffness, maximum load, and post-yield deflection together contribute to work to fracture. And so that's why it looks like this in that diagram, okay? Because it's literally just the summation of those three variables. Now, one thing that wasn't in the original paper is this dashed blue line. And this is research that has happened since the writing of that paper, where we've come to realize that brittle bones that tend to break in a more brittle fashion, like chalk, they tend to be weaker, okay, or they show up as being weaker. And we're not really exactly sure why. There's still a lot of work that needs to go on to them. And that's why I put this dashed line here, that this is something we want to be on the lookout for, is that as your bone becomes, if you have a smaller PYD or more brittle, it may start seeing decreases in strength. Okay, we see this in the human skeleton. I've seen it in the mouse skeleton. We published on the human skeleton, but we haven't published on the mouse skeleton yet, okay? Now, going back to morphology, I think most people here are somewhat familiar with moment of inertia. So moment of inertia are important for long bones where they're subjected to torsional or bending loads, and where the distribution of the tissue starts becoming more important than the amount of tissue or the area. So this is a diaphyseal bone we can represent as a cylinder, and as if you took a cross section of that, it would look kind of like this ellipsoid, where the bone is represented by this dappled feature, has the periosteal on the outside surface and the endosteal surface on the inside, and this is the cortical bone itself. I'm not going to go into all of the equations to calculate moment of inertia. A lot of these things are more automated now in the image analysis software suite of most micro-CT imaging systems. But some of the area traits that I tend to look at are total area, which would be everything within the periosteal surface, cortical bone or area, which is just that, which is this gray part, and marrow, which is within the inner part. Those are the three ones that I primarily look at because it tells you something about some of the biology. So the total area, so you start seeing changes in that, especially if you have something that perturbation that affects growth-related processes. It's going to tell you something a little bit more about factors that are affecting periosteal expansion earlier in life, and that's an important feature of bone. Cortical area changes would point you to something affecting mass accumulation, and that could come from both an effect on the periosteum as well as the endosteum. The marrow area would point you to things that are really affecting either marrow expansion or infilling. So if you're familiar with the growth process, as let's say a cortical bone, it's going to grow outward, but it's also going to drift. And that is something that's well known, but it's something to kind of pay attention to if you're trying to relate some of these phenotypic measures to the biological measures, that a change in the marrow space could come as a result of the combination of osteoblastic activity as well as osteoclastic activity. And the same thing could be said for periosteal surface. Okay, so just to kind of bring home the point about motor inertia, most people are kind of familiar with this analogy. So if you take a simple ruler, which is flat, and you bend it with the flat edge down, it's very simple to bend it in this direction right here. So it has a low resistance to bending, whereas if you just rotate it 90 degrees, and you have this profile against the bending, it becomes quite stiff. So in both of these cases, the area is the same, but the distribution of that material relative to your loading is very different. So this kind of structural feature will be more resistant to bending compared to this one. So that's why moment of inertia can be an important feature of bone to kind of pay attention to, in addition to things like area. So this builds like this part of that biomechanical mechanism where total area, cortical area, and marrow area are just related to each other mathematically. That cortical area is just simply the total area minus the marrow area. And moment of inertia is, this is the equation for that. It's related to the fourth power of the radius. And so it depends both on the outer bone size as well as the amount of tissue. That's why there's both arrows in that direction. Okay, so now we're going to move on to tissue level mechanical properties. So we talked a little about whole bone mechanical properties, and this is where we want to be a little bit more precise with some of the language that we're using regarding mechanical testing. So whole bone mechanical properties would be things like we described before: stiffness, maximum load, or we'll use whole bone strength, and then postural displacement and work to fracture. And these things come from mechanically testing the entire bone, in toto. Now, if you're able to machine beams of bone from these tissues, whether it's a preclinical model like a mouse bone or a rat bone or even human tissue, you can create things that have a more regular shape to them. And you put those into a similar fixture. It could be like 4-point bending as I've shown here. And you can do the similar kind of testing, but the outcomes are a little bit different because they tell you something about the material itself. So whether it's more like aluminum or steel, okay, well, there are very, very different material properties. We can do very similar things looking at the tissue in bone as well. But the properties there are, they're called a little different. Instead of whole bone stiffness, it's really tissue level stiffness or the elastic modulus. Tissue level strength, which can often called ultimate stress, post-yield strain instead of post-yield displacement, and then toughness would be the equivalent of that for work to fracture. Okay, and so that rounds out these elements of the biomechanical mechanism. So you have your modulus, your strength, fatigue, strength, and fracture toughness, and each of them have some sort of effect on, let's say, postural deflection, which is really related down toward the tissue level fracture toughness and fatigue strength. I didn't really talk about fatigue strength, but that is simply just when you do the same kind of material test, instead of the failure, you'll do 1,000,000 cycles of a low-level displacement, and then measure how long does it take for that bone, or how many cycles it take for that bone to fail. These are important more, rather than just a simple monotonic failure to test, or failure test like I was just describing. They tell you a little bit more about the endurance of the tissue, okay, and how it's able to take 1,000,000 to 2,000,000 cycles a year like we do when we walk, and why these tissues really do not fail. And a lot of it is because we have biological processes that can go in and repair damage that might be accumulating within the tissue. So we included that one in this diagram as well, because we thought that's also an important feature of these biomechanical mechanisms to consider. Okay, and so now what I want to do is kind of shift a little bit over to back to the morphology for a little bit and talk a little bit about something we call contextualized biomechanics. Now, we've not published on this concept specifically. It's been kind of hard to kind of, wrap our heads around this. And with a little time, maybe we can develop some sort of review paper on this. But the general idea is that, it really describes how a change in one bone trait may affect strength, that relationship may depend on another trait. And I'll use porosity and cortical thickness as an example. So we developed something called a cortical pore score, and there's a publication right down listed down here that describes where that came from. And we were kind of interested in understanding that if you had a narrow bone that looks like this is a nano CT image of a human radius. Okay, and this is the narrow version of that bone, and this is a wider version. It's from two different individuals, 71 to 74 years of age. And we were curious to see, if you had a pore in this bone, which is actually pretty close to the geometric centroid, versus a pore in this wider bone, which is much, much further from the geometric centroid. So the presence of that pore in the wider bone, we would hypothesize to actually have a more deleterious effect on the overall strength. Okay, and so the cortical pore score was just an attempt to quantify that effect. So when we looked at these two images, I couldn't get two cross sections with the exact same porosity. So you're gonna have to work with me on how to build out this story. So this narrow bone obviously has a smaller total area, which is everything within the periosteal envelope. So it's, there's a 1.4 difference between those two. Porosity in the narrow bone was a little bit lower, about 7% versus 22% in the wider bone. So the difference there is about 3.2. But when you start looking at the cortical pore score, which is a summation of the area of the pore times the distance squared. So this would be similar to how much of that moment of inertia is taken up by pores. So that's why you're starting to see a fourth power to this association. So what you see now is that the effect of pores is 9 times different here. So we would expect that a bone with the pores in the wider bone may have a more deleterious effect on overall strength. So we can say that something very similar for cortical thickness. Now, in the way I'm bringing this up today, though, is what we often see in a lot of papers, and especially in preclinical models, is that let's say you're looking at a particular genetic perturbation, and we get you often see that this gene led to a low bone mass phenotype. Okay, well, when I read those papers, I thought, oh, that's interesting, and then I want to learn a little bit more. It's like, okay, so tell me more. Like, how did this low bone mass phenotype come up, and how is it manifest in its morphology? Okay, so we can play out a couple of different scenarios to kind of give you an example of why you want to dig and tell the story in a little different way than just say a low bone mass phenotype. So for example, let's say this is your original cross-section of a bone here. Gene X was applied in some way. And what happened in this particular scenario is that you just had increased marrow expansion. Okay, so it's less bone mass, so less cortical area, so you would expect a lower strength. But if that gene X had a low bone mass phenotype that looked like this, you'd expect a much, much larger reduction in strength because it had both the effect of an outer bone suppression as well as maybe a lower mass accumulation. And to me, that's giving a little bit more insight into what was the manifestation of that gene on that overall bone strength. Okay, now that we are complete experts on contextualized biomechanics, I'm going to shift us over further, okay, to complex adaptive systems. And this is an area that we kind of stumbled upon about 25 years ago when we started looking not just at differences between groups of mice, but trying to understand why some are more similar. Okay, believe it or not, this will make sense in a minute. So complex adaptive systems is just simply a framework for studying dynamic networks of interactions among traits, okay, that together they have to work together to combine to establish overall function. So when we look at how these phenotypes and perturbations work. We're looking at it in a more holistic way. Again, looking at how the system is adapting to a perturbation and whether or not other changes have occurred along the way. Establishing the causal relationships of that is very difficult. In the past, we did a lot of things like path analysis, trying to figure out some of those, at least trying to establish a reasonable approximation for how these things are related, even if we couldn't get definitive causality. So basically, the framework is kind of set up like this. You think about a variation or perturbation that is very meaningful to you, okay? And I'll explain what was meaningful to us in a second. And then you start looking at, well, how did the bone deal with that variation? So what changes and traits that happened that look like they're coordinated, okay? And then the summation of that will give you the set of traits for that particular genotype, and how that's then leads to system level function. Okay, so as I mentioned, we did a lot of path analyses about a couple of decades ago. We were really trying to establish these associations among different trait features. And so instead of just looking at individual traits as an outcome of these micro CT and nano CT analyses, we started looking at things that more about how they're interrelated and how they're coordinated. Okay. So the variation or perturbation that we were interested in was really about how wide the bone is. So nature allows for a lot of variation to happen. When you look at bone, you can have like a narrow phenotype all the way to a wide phenotype, and this is all normal. Okay, if you look at across individuals, not everyone has the exact same bone structure. And so nature has figured out a way to deal with the fact that some are narrow and some are wide. And, it's kind of a Gaussian distribution. So the majority are somewhere in the middle. Okay, and this variation is established early in life. A lot of it is genetically determined, but a lot of it is also environmentally modulated. Okay, we've known that from different types of adaptive responses that we see in the outer bone size. Okay, and the reason why this is important is because small changes or small differences or variations in external bone size have a disproportionately large effect on strength. We talked about moment of inertia, and so the bending strength is somewhat proportional to the third power of the outer diameter, okay? And so you can see that the nature would have to really shift a lot in order to accommodate that level of a variation. And that's what we spent a lot, like 2 decades kind of looking at. So if people have seen me give this talk before or a variation of this talk, you've often seen this particular analogy is what I like to refer back to bikes. And Shoshana Yakar, I noticed, was on here, and she has seen this this talk several decades ago when we were at Mount Sinai together. So in one sense, you have bikes that have this narrow tube structure, and they often are built of steel. And the other extreme, you have bikes that use aluminum, and because aluminum is less stiff on the material level compared to steel, it has to use a larger diameter in order to accommodate the lower material stiffness. And you have bikes that are made everything in between that. Well, bone does a similar thing, is that the narrow bone phenotype looks more like this. We call it slender or narrow because we often adjust for bone length. So we're not really saying that this is a smaller or shorter individual. We're taking height and stature out of the equation at this point. But they, on average, on an absolute basis, have a lower cortical area, but a larger relative cortical area. So by what that I mean is that if you just look at cortical area itself, it should be lower than the wider one. But relative to total area, it's higher. So when you take the ratio, you'll see an increase in relative cortical area. They tend to have a thicker cortex. Often, we see lower porosity and sometimes even higher mineralization. We've seen that in mouse bone and we've seen it in human tibia, but it's not replicated in all bones. And we find that this phenotype tends to be a little bit more brittle, and sometimes that comes from the lower porosity and higher mineralization. Now, on the other extreme, we see this wider bone. Okay, so it's a higher amount of cortical area, lower relative cortical area, thinner cortex, higher porosity, and lower mineralization. But when we break these bones, they tend to be tougher. And that could be because of lower mineralization, but we're not exactly sure. Okay, so this is a preclinical mouse model example. Just want to give you an example that these principles apply to human tissue as well. So what you see here is a PQCT images of a human metacarpal. This is a PQCT image of a human tibia. So the narrow phenotype, as you can see here, is pretty dense looking bone, very small narrow area compared to the wide bone phenotype on this side. Okay, so we see this replicated, this concept replicated between a preclinical animal model as well as clinical human model. And so we see that, so when we're studying animal preclinical models, we can take some of these principles and apply them to humans, which is a really nice feature of this. Okay, so why is this important and why am I spending so much time in this? And the reason for that is that we have found this is very helpful for us to interpret what's going on. And often when you're looking at a perturbation, you're trying to compare an experimental outcome back to a reference population. In animal models, you are often comparing it back to a control, which is unperturbed. So the comparisons usually tend to be more direct. If you're looking at human populations, it's a little bit more challenging because what is your reference population? And I'll kind of also show you with this. So when I think of a population mean, a lot of people just think of a mean and a standard deviation or 95% confidence interval, so like a point in space, okay, with little brackets on it. When I think of a population mean, I really think of a spectrum. Okay, so we have this narrow bone phenotype all the way to this wider bone phenotype, and they're different. So we have apples on this side, oranges on this side, if you like fruit. And we don't like to compare the narrow bone directly to the wide unless you're really doing a preclinical animal model. And I'll explain why, because they're built differently. Okay, so if you're looking at deviations from this phenotype, my recommendation is that if you have a narrow bone phenotype, if you have a population with other individuals with narrow bone phenotypes, and you're trying to understand, do they have lower than expected bone mass? If you compare it to the population average, you might get a different outcome than if you compared it to a similar external size specific subcohort, okay? Because that's what we're really trying to understand is that if you're going to compare this bone to the middle, you may not see the outcome versus if you're looking over at this end, the wide bone, they have a higher cortical area on average, and so you may not see the lower bone mass phenotype if you compare it backward to the reference population. So we would advocate on this one to compare to similar external size phenotypes. Okay, so how does this work in a practical sense? Let's say you have a perturbation, you're trying to understand what's going on. So let's say this is your control, you have a bone cross-section that looks like this, and this is your experimental, and it moved over here. So a direct comparison, again, going back to this idea that, the perturbation led to lower cortical area or lower bone mass. Okay, what I would recommend doing using this kind of, pattern is first saying, well, was there a change in the outer bone dimension here? And the answer is yes. It became more narrow. Okay, and was there then a difference in its cortical area? Was it where was it expected for that phenotype? Was it higher or lower? In this case, it was lower. So you have kind of a combination of two things going on. So the perturbation led to both a lower cortical area, total area arising likely from suppression and periodic expansion during growth. And that was combined with a lower than expected cortical area for the narrow bone phenotype. So something that you would want to look at further on down the road is what's also inhibiting bone mass accrual in this animal mouse. Okay. So another thing to consider too, and this is what I've often seen in some papers, is lack of consideration of body size effects or even reporting out on body size. So body size is really important for bone because bone is actually quite sensitive to that. So the general idea that bigger mice tend to have bigger bones is very true. So a lot of genetic perturbations, we often see that the experimental mouse is like say a 10% lower body weight on average. And then often you see a 10% lower stiffness, 10% lower strength, 10% smaller cortical area. And so when I read those papers, I'm like, okay, they didn't adjust for body weight. How am I to interpret this? Did the perturbation just lead to a smaller mouse? Okay, and so this is where the digging really has to come into play, is that, trying to adjust for your body size effects is actually quite important. So I'm just going to go through an example of what we do Okay, I am going to put a disclaimer out there. I'm not a statistical expert, and so I'm just going to give you a couple of examples of what you could do. But I would also, if you're interested in doing this, consult with a statistician and get some expert advice on this. So in this particular example, what we have here measured as cortical area of a control and experimental group. If you just report the unadjusted data, you would conclude that the perturbation led to lower cortical area. Great. But what I normally do when I get the data is the first thing I want to do is take my kind of body size sensitive measures like cortical area, stiffness, strength, and plot them against body weight. Is there an association there that we should be concerned about? In this particular example, you can see that cortical area lines up very nicely with body weight. Should there be a linear relationship between these two? I don't know. And this is part of one of the limitations of our understanding as a field, trying to establish these associations is still underway. Okay, but you can see that the regressions kind of overlap quite a bit, okay? You can calculate the average body weight between the two, so it's the average of the averages in this situation. And I usually use this method here, this linear regression method. Very simple, it can be done in Excel, okay? And what you end up getting then is there is no difference between the two. The perturbation just led to a smaller mouse, but it did not affect bone mass accrual. So that's still a valid interpretation of this data. Okay, so I'm going to run through an example. I was kind of scouring the literature to come up with a couple of examples that weren't mine. And then I started thinking, well, if I was on this call and someone was going through my study, I would get a little nervous. I didn't want to put anyone on the spot, so I'll put myself on the spot, okay? And in this particular study, we were looking at two different strains of mice. My two favorite ones are the AJ and the B6 mice. In this particular experiment, what we were looking at is young mice exposed to voluntary cage wheel running. And we were trying to understand, did this AJ, which has this narrow bone phenotype, does it respond the same way to running compared to this B6 mouse, which is a wider bone phenotype? So in this experiment, they were 4-week-old female mice, voluntary cage wheel running unrestricted, and they ran for about 4 weeks. So we're looking for kind of early effects of exercise. The mice run a lot on these cage wheels, about 6 to 7 kilometers a night, which is quite remarkable. I don't do that. I don't think I've ever done that, even when I was young. So we looked at their morphology, their nano-CT, using nano-CT, we broke their bones, using 4-point bending tests. And in this particular situation, we did general linear model analysis of variance with body weight as covariate to adjust for body size. Okay, and I'm just gonna run you through the data and then how we interpreted it. So this is the AJ mouse, and its bone right here, as you can see, it's kind of that narrow bone phenotype with a proportionally thicker cortex compared to the B6 mouse, which is kind of a wider bone phenotype and proportionally thinner cortex, okay? So here's the control bone and the exercise bone, control and the exercise. So I'm just gonna go through each of these. What I normally do is start with the total area, kind of work outward in. So total area will tell me something about what's going on with the periosteum. So in this situation, remember, this is the body size effects have been adjusted in this. So the control for the AJ mouse, we saw a very small, slight increase in total cross-sectional area. And there's a reason why I'm reporting it at 0.06. And a couple more clicks of the mouse here on my end and explain why. But what's interesting is that the exercise mouse for the B6 actually showed a lower total area. So the interpretation is pretty simple. A slightly increased total area for AJ and a decreased total area for B6. Somehow the exercise was suppressing periosteal expansion in the B6 mouse. When we looked at marrow area, we saw no change in the AJ mouse and a decrease in the B6. And then this is where it was really important to look at even subtle differences, is that the cortical area in the AJ went up. Okay, so you can start seeing a significant difference in one of your measures, even though another measure might be kind of on the cusp, because a small difference here can actually lead to a larger difference over here in cortical area. Okay, and in terms of for B6, it actually sort of decreased. So exercise led to a more narrow phenotype in the B6 and lower cortical mass. However, when we broke the bones, the AJ showed what you expect of a kind of an anabolic stimulus, an increase in strength. Whereas in the B6, no adverse effects. So when we put these on this kind of grid that I was showing before with all the circles, this is the AJ phenotype here, and it kind of went upward or even maybe a little bit to the right here and then over, okay, in terms of it's a little bit wider and more mass. Whereas the B6, surprisingly, moved to a narrow phenotype and maybe a little bit down in terms of cortical mass. Okay, so that's how we interpreted this. But it was interesting, if you reverse that, that discussion about the B6, I think people who don't exercise may appreciate this, is if you don't exercise, you get a wider bone phenotype with more bone mass in the B6 mouse. Okay, so that's the irony of that. Okay, so I'm just going to sum this up and then we'll open this up for discussion. Okay, so what I tried to run through today is really making best use of your morphological data and how do you relate this to whole bone mechanical function. You need to really understand some basic biomechanical principles. That's really important. Be on the lookout for contextualized effects in strength. So when you're reporting out in cortical thickness and porosity, please also include how they're grounded to, let's say, external bone size, because I think it's helping to better understand the impact of that change on strength. Understand bone as a complex adaptive systems, compare apples to apples and oranges to oranges. So if you move into a narrow phenotype, compare to other narrow bone phenotype mice will help you better interpret what those changes. Please do adjust for body size. This can be kind of an annoyance, but even if you see 5 to 10% differences in body weight, they actually do make a difference in the outcomes of your data. And then the next is, what are next steps? Follow up on your morphological data. So this is the cliffhanger part of your detective story. And this is really important to confirm or refute, some of these outcomes. Tissue mineral density is notoriously problematic in micro CT and nano CT systems. If you see a difference there, please do confirm that with Raman or ASH content to know whether or not it did or did not have some sort of artifact. Total area and mirror area, dynamic bone labeling, something that this field is quite familiar with doing. These are really helpful to understand how that's related to whether osteoblastic or osteoclastic activity or some combination of the two. And then finally, the same principles you can imagine can be moved over to a metaphyseal region. Something like this right here is a mouse vertebral body. It has both a cortical shell, as you can see, as well as a trabecular core. What often happens, even if you look at, let's say, a distal femur or proximal tibia, often what you see is report out on the trabecular bone traits. And when I look at that, I'm like, okay, that's great, but the two of them together define overall function. Okay, so here's an example of different recombinant inbred mouse strains where they have different combinations of cortical and trabecular, and even one to the point where it almost looks like it has very little trabecular bone inside, and yet this is actually quite a strong phenotype. And a lot of it is because the cortical shell takes up and accommodates for the lower trabecular bone phenotype. So the general idea here, though, is analyze them separately to get your traits, but then integrate them during your interpretation phase to understand the impact on strength. Okay, so I'm going to give a big shout out to all my collaborators. There are many. This is one of the nicest things about being in academic medicine is that we get to work with a lot of people around the country, a lot around the world. And I also want to also end with some references and resources. So those are the two references up there that we've referred before. These are some simple guideline papers. If someone would like to take on the task of doing another guideline papers for cortical cancella structure, it's wide open. And I think the field would be very appreciative. And the other thing I want to point out, here's a QR code. In our core center at Michigan, we often use Dragonfly software. So I'm not promoting this because I don't actually have stock in the company. Okay, just wanted people to know that, but we use it and we work collaboratively with that group. We do have some validated, fully convoluted neural networks that can make your life easier. These things can be used to segment bone from background. They can be used to segment cortical from trabecular bone. This one is an example of how we can take a whole human proximal femur and have a validated bone to background segmentation, which is really important, especially for larger structures. And also the cortical trabecular segmentation seems to work really well. What's nice about this is that we're doing this in a community-based method. We have some collaborations with folks at Colorado and Ohio State, and we are trying to continually improve these neural networks with new tissues, samples that are scanned in different micro CT and nano CT systems, so that we can develop this kind of community-based neural network. And I also want to put a plug out. We have over 200 nano CT images of human proximal femurs that are available for public use. So anyone would like that, just contact us, and we are putting them onto a public accessible server, and they would be available to the community for use. Okay, and so with that, I will stop sharing, and hopefully I didn't take up too much time. And if anyone has any questions, it'd be great to hear. Oh, thanks, Melia. And Maureen.
That was great, Dr. Jepsen. Thank you. And it was really good timing. If anybody has any questions, you can unmute yourself and ask, or just put it in the chat.
Hey, Karl.
Yeah, hey, Rick.
Rick Sumner. So I
How you
really
doing?
enjoyed that. Thank you. Could you maybe comment a little bit on controlling for body size in trabecular bone versus cortical bone? And I noticed you didn't mention allometry at all. So
Yeah,
you want to
didn't
have
mention allometry. That's a tough one, right? And I think this is where, we think back 20, 30 years when we were really doing a lot of phenotyping in mouse, and we probably should have taken this on as a field, right? And trying to figure out what is the best way to adjust for body weight. And so I'm just doing things that we did a long time ago, Rick, as you know, and I don't know if it's the right thing, but it's just trying to get at, is there a body size effect that I'm dealing with? Right. And what we do with human tissue, we do the same thing. But the statistical approaches are a little bit more sophisticated there because we're working with statisticians who know what they're doing. A lot of the mouse phenotyping stuff is just me working with Excel and doing things that way. So I don't have a good answer to you on allometry. But based on your background, you might actually have some good suggestions. What do you think?
maybe just go back to the trabecular, controlling for
Oh,
body size on trabecular bone.
yeah, that's a good question. And again, I would, if anyone, has ideas about doing another guidelines paper, that would be another area to explore. I don't have a good answer to you. My only approach would be this, is look at your data the same way I've done it. Take your cortical traits, plot them against body weight. Even if there's a linear or nonlinear relationship because of allometry, you're going to start seeing an association. And with trabecular bone, sometimes you don't see it. We've done this with human tissue and have not really seen trabecular bone to be super body sensitive. So if there is no association and you try to correct it using that linear regression method I showed you, it ends up doing nothing to the data. Okay, so it doesn't hurt to do it. Okay, I still think there's a lot of work that has to be done, and you are 100% correct. We don't know that association with trabecular bone.
All right, thanks.
Karl. Okay,
Hi,
sorry,
Karl.
Rick.
Carl here. Yeah, good to see you. Nice talk.
Thanks.
So I have a question about the sort of genetic determinants of these differences in cortical bone organization that you've seen. I know you've done a lot of work on that. I'm wondering if you could speak to what are some of the key genes, and are there any that are related to cells? And it's you might expect from me specifically the osteocytes. Like what are some of the determinants here?
Karl, it's funny that you're asking this question because I think you're probably a better person to answer your own question than me. I I put down the mouse bone about a decade ago and shipped over to humans, and so I've not been monitoring that literature. So I'm sadly not going to be able to answer your question very well. Obviously collagen is really important, and we see OI phenotypes where, osteogenesis imperfecta phenotypes where the impact is huge, right? But I don't think that's what you're asking for right now, are you?
Not exactly, but point well taken. And then I wonder, like, if in the humans you see any clustering of genes related to bone robustness.
Oh, that's a good question. there hasn't been a lot of work on outer bone size. Okay. I'm scanning. I knew the literature a long time ago. There was a study with Bulgarian twins that was done, I don't know, in the 80s or 90s, where they're looking at difference between those to what extent is external size a genetically determined trait. And it was pretty high. I think it was 60%. We looked at it in the mouse. It was pretty high. Do we know the genes? I don't know the genes. I don't know that people are looking at that, unfortunately. But
Fair
great
enough.
question.
Thank you. Thanks.
And sorry for not having the answers to your question, sir.
I have a
Karl,
couple
this is,
questions. Oh, sorry.
oh,
Oh,
sorry. Yeah,
hey,
Shoshana,
Shoshana.
Karl, how are you?
I'm good. How are you? It's been a
Good,
long
good.
time.
Yeah, I wanted to ask you about, so you were like emphasizing the body weight. However, I have a lot of models that I see effects of body composition, in fact, like increased body adiposity, and increased body weight, sometimes does not relate to bone mechanical properties. So
Yes.
what's your take about this?
That's a great point. So we use body weight because that's what we had. We did not have body comp. And there are studies that are showing that lean mass is probably a better way to adjust than total, right? And again, and if there are other people on this call who have more experience with that, I would love to hear their thoughts on it. We often don't have body comp data to work with. And I know, in Shoshana, some of your models, you know, because if you start seeing difference in adiposity, that could be another factor affecting the bone, either as a mechanical variable in weight or as a biological variable, right? And
Yes.
yeah, teasing that out would be really important. I think there's a lot of people looking at in terms of in human bone and obesity, right? Yeah. I don't know. Does anyone else on this call have a better understanding of these associations?
Mm-hmm.
Yeah. I have not had a chance to look through any of the data myself, so
Yeah.
don't have any personal experience.
Okay. Thank you.
I'm sorry. Yeah.
I know that we're almost out of time, but we have a couple questions in the chat, Dr. Jepsen. I don't know if you can see them or if you want
Oh,
I can
yeah.
read them for you.
3-point versus 4-point. We did 4-point bending primarily because we didn't want to determine where it would fail. And 3-point bending, it will always generally fail right underneath that center point. And so we used the 4-point because we wanted to fail wherever it needed to fail in that region. So that's why we chose that. Thank you, Michael. Do you see the role of machine learning playing out here besides segmentation? Any comments on these tools? Yeah, so if you're talking about machine learning in terms of the development of neural networks for segmentation, I drank the Kool-Aid on that for sure. We were always traditional segmenters, you know, doing it manually, I thought was the best way to go, but the machine learning is much more rigorous and reproducible. And once you put the effort into learning how to do that, which I think we are moving in that direction, the models just get better, better, and better. And then we just have to correct them every once in a while. So our outcomes are even more precise now than what we did, you know, a couple of decades ago. Ashlyn, phenotype where the mouse is gaining visceral fat leading to body weight. Yeah, that's the same question as Shoshana. I don't know. I think as a field, we really need to kind of tackle this question. And you know, maybe we can do this collaboratively too with a lot of data, because this is a big data kind of question, I think. Okay, Heidi, is the imaging data good enough to calibrate for density and add this to factor in analysis? I would say, in terms of, if you're talking about like bone mineral density equivalent to the clinical thing, I would say be careful. Tissue mineral density, which is essentially the gray value of your micro and nano CT systems, be very careful with that. They are prone to partial volume effects. And what we did was that we took hydroxyapatite mimicker little sticks, machined them with a little isomet into, like, you know, 50 micron by 50 micron sticks, 100 micron, 150, and then put that into the micro CT and nano CT systems. And what you see is that the smaller the stick, the lower the tissue mineral density, even though they have all the same mineral value, okay? So the size of that feature in some ways could affect your mineralization, so be careful with that. I always recommend if you see a TMD value difference, follow it up with Raman or ash content. Thank you, Saidmadi. I'm sorry if I'm mispronouncing your name. When addressing body size, we correctly assuming that two individuals have similar body size. Wouldn't this be wrong premise in some cases, for instance? Yes, good question. So yes, body stature can have two different factors, right? You know, and in fact, you can get more than just that. So height as well as weight. And often, like when we're using human or data, we often don't have both. We have often sometimes adjusted for body height because over time, that seems to be a variable that doesn't change nearly as much as body weight. They tend to be related, but again, this is an area that I think when I look at our human data, where I think that we have our most vulnerabilities, and so always trying to interpret that information with caution. Okay, Benjamin, from a statistical standpoint, is it valid to look for relations between both measurements and BMI? Yes. Again, it seems like this group is really interested in body weight adjustments. I know Matt Silva's group is doing a lot of good work in this area. You know, maybe we can coerce him to doing a follow-up on some of this, or that could be a whole seminar on how to do this. I don't have good answers for this group on the body weight adjustments, BMI, body comp. I'm sorry, I don't. We just do very rudimentary adjustments because we feel that at least we're course correcting in a coarse way on that and not maybe in a refined way. I don't know that we're ever going to get to that refinement that I think some of us are looking for. Okay. Did I get through all the questions in rapid?
Yeah, right on time. Thank you so
Almost
much,
talked as fast as you
Dr.
as
Jepsen.
Carlos.
It was great, fantastic presentation, and thanks everyone for attending. We hope to see you in next month's seminar, and thank you again, Dr. Jepsen, for the great talk.
Thanks, everyone. Good to see you all.